All right, let's take a look now at differential equations as mathematical models. Although mathematicians tend to like to study things for their own sake, we like the rich theory that comes from studying these objects in their own right. There is a lot to be said about the utility of differential equations outside of just its theory. One of the greatest applications of differential equations is using it as a mathematical model, as a way of expressing a real situation in a mathematical form so that we can then study the effects of those systems. So first of all, a little vocabulary, a little bit of nomenclature here. A dynamical system is a system of time-dependent variables. Everything we look at here will be dependent on time, and we're going to be looking at continuous and as opposed to discrete time. Is a system of time-dependent variables. Everything will depend on some parameter t. These are called state variables. These time-dependent variables are called state variables. Along with a rule that allows us to, I misspelled the word to, isn't that impressive? Allows us to unambiguously determine the value of all of these state variables when you have all of the values of these variables, you call this the state of the system. The state of the system at some time t. At some time t, where the state at some initial time, which we denote as t0, where the state at t0 is the set of initial conditions. So this will be an initial value problem since it has initial conditions. If you have the solution to the initial value problem, this system along with its initial conditions, the solution to that initial value problem is called the response of the system. These dynamical systems here that can be classified as either continuous or discrete, whether that is to say you can look at time in the continuous variable or discretely, 1 minute, 2 minute, 3 minute, 4 minute. Here we'll be looking at things continuously, but there are ways of looking at them discretely as well. Okay? So there are lots and lots of different kinds of applications to differential equations, lots of different things that can be used, lots of different things that can be modeled using these differential equations, these dynamical systems. So here we're going to focus on a very particular subset of problems here. We're going to be looking at ones that involve fluid, that involve liquids being mixed and moved around. And as our first example, let's go and take a look at this. Incidentally, the choice of problems that involve fluids is an arbitrary one. These aren't particularly special or important compared to any of the other ones. It's just this is such a very deep subject here that could cover an entire career as an engineer, as a physicist, as a mathematician. So here we simply choose a very small subset of something to get us started. Okay? So our first problem, a very visual one, which in fact we'll even draw out here in a moment. Suppose you have a large mixing tank, just a giant container that will hold water. It initially holds 300 gallons of water. Now, it's not full. It can hold more than that, but at the beginning, it has 300 gallons inside. Initially holds 300 gallons. Let me write this whole thing out. Gallons of water. Into which 50 pounds of salt has been dissolved. Dissolved to make a brine solution. A brine solution is just what is a formal word for salt mixed in with water, to make a brine solution. Okay. Now, we're going to take another brine solution that is not the one that's in this tank. It's coming from some other place. Another brine solution is going to be pumped into this tank. It's going to come in and join this water. At a rate of 3 gallons per minute. The solution is well stirred. When they say the solution is well stirred, all that means is that everything is uniformly distributed. There's not going to be any pockets of salt where, all the salt's on the bottom, so we have to consider that. Well stirred just means everything is uniformly distributed. The solution is well stirred and simultaneously, and that is important, simultaneously is pumped out at a slower rate of 2 gallons per minute. A bit of clarification, simultaneously. What that means is you don't put the water in, stir it, and then whatever you have in there, you pump it out. No. At the same time that some water is coming in, some water is also leaving. So both of these are happening at the same time. As some brine solution comes in, other brine solution is leaving, and you're not waiting for one to finish before the other starts. Okay? So here, it's going to be pumped out at a slower rate of 2 gallons per minute. Okay, now, if the concentration of the solution of the incoming solution, let's say it that way, of the incoming solution, the one that's coming into the tank, incoming solution, is 2 pounds per gallon of water, 2 pounds of salt per gallon of water. The question is to determine a differential equation for the amount of salt, which we're going to call A of t, A for amount, T for time, so the amount at time T, in the tank at any time after the initial experiment started here. In the tank at T greater than 0. Okay. For any of these types of problems where you have a physical phenomenon happening, it's not a bad idea to start by giving a simple elementary sketch. You don't need to be good at drawing, but it does help you organize your information. For this problem is still relatively simple. We're just getting started, right? But in later parts of the course, we are going to look at some more complicated problems with more stuff going on, and in those cases you really want to have an illustration to organize all your information to make sure you're using everything, not forgetting anything, and it's a good idea to get yourself in the habit even early on. So here we have a tank. And this tank currently is holding 300 gallons of liquid. Now it's not full, there's more room for water because we're going to have to bring some in anyway. But for right now, there's 300 gallons of water. And there are 50 pounds of salt that are mixed in. Now you have some pipe that's bringing water into your tank. Your water is going to come in this way. Okay, well this is going to come in at the liquid will come in at 3 gallons per minute. So this is 3 gallons per minute. But now for each gallon that comes in, the concentration is 2 pounds per gallon. Okay? So this is 2 pounds per gallon. So the amount of water coming in per minute and the amount of salt coming in per gallon. Now, as this happens simultaneously, you're not going to wait for this to fill up before you do this, but at the same time, there's another pipe that's pulling water out of our system. And this is leaving at a speed of, where was that? 2 gallons per minute. So over here, this is leaving at 2 gallons per minute. Okay, and that's all the information that's given to us, I believe. Yes, that's all the information that's given to us. So now the question is to find a differential equation that models this scenario. Okay, so every person has a different way of organizing their information. You'll find that my way, and not just now, but for problems in the future, later parts of this course, you'll find that what I generally tend to do is draw something out and then start with a kind of a big picture type formula, a big picture type of equation, and then add details as I go along. This is definitely not the only way to do it. It may not even be the best way to do it, but this is the way I do it. So what we want to do is we want to find something about the salt in the tank. All right, we know it's 50 pounds to start with, but that's quickly going to change because salt will come in, salt will go out. Okay, so we would like to find an equation for the amount of salt, but we can't get that directly. What we can easily get is the change in the salt, because we know some's coming in, some's coming out, and we know the amounts that are coming in and out. We know the rates and everything. Okay, so without any details, just overall, what's the easiest thing to get in relation to the amount of salt? It's going to be the change in the amount of salt. I know some comes in, I know some leaves. So positive minus negative, yeah? Okay, so change in salt. All right, well, how do you get that? Well, okay, I'll have details later, but for now, it's basically just the input rate of salt minus the output rate. If I have 50 pounds coming in and 45 pounds leaving, I have 5 pounds every minute that gets added in. So input rate of salt minus the output rate of the salt. Okay, so now let's be a little bit more specific. Change in salt. Well, the amount of salt is A, and ever since Cal 1, we know that change in something, that's a derivative. Right? The rate of change of something is its derivative. So salt is A of T. Change in salt must be the derivative of A of T. Okay, so it's the derivative of A with respect to its variable. The variable is X. The variable is T, not X. So here we'll say dA dt. Okay, so there we go. Symbolically, that's the change over time of salt. That's equal to the input rate of salt. Okay, well, let's see. What's the input rate? Oh, well, let's see. We have 3 gallons every minute coming in. Okay, so that's 3 gallons per minute. Oh, but that's the amount of water, not the amount of salt. Oh, but that's related. Because after all, for every gallon, I'm going to put in 2 pounds of salt. For every gallon of water, there's 2 pounds of salt. Okay, well, if there's 3 gallons, 3 times 2 will give me 6. So here, if I multiply these together, that's 2 pounds of salt for every gallon, and there's going to be 3 gallons. Okay, so 6 pounds of salt. But notice that's a rate. And in fact, here, by writing out my units, I can quickly see that that actually is the unit that I'm expecting. Right here, this ends up being pounds per minute, which is what I want. It's an input rate. Rate is per minute or per hour, or per unit of time. And since we're talking about salt, salt is being measured in pounds here. So input rate of salt is going to be 6 pounds per minute. Okay. Minus, okay, now the output rate. The output rate's a little more complicated because I don't have all the information yet. The input rate is, okay, here's how quickly the water's coming in, and here's the concentration of salt in that water. Okay, over here, here's how quickly the water is leaving. Okay, so I do have that. It's going to be 2 gallons per minute. But then I would need to multiply it by the concentration of salt, just like over here. It's rate of water flow times concentration of salt. Rate of water flow times concentration of salt. I don't have that. Now you might think, well, it's 50 pounds dissolved into 30 gallons, right? Well, no, because there's water coming in with salt. So the concentration in the tank is going to be changing. Okay, so that's not a constant number. I can't just multiply by 50 over 300. I have to write this as a variable. Okay, well, how do you find concentration? Oh, well, concentration is pounds of salt per gallon. How many pounds are in here? Well, it starts off at 50, but it's not going to be 50 the entire time. So here we have some unknown amount of salt. It won't always be 50. Oh, well, we have a symbol. Even though we don't know what the amount of salt is, we have a symbol for the amount of salt. So that's your A of T. That's the number of pounds of salt you have. It's an unknown for now, but it goes right there. Divided by the number of gallons you have. Oh, well, gallons is, that one's a little easier. I started off with 300 gallons. Now, every minute, I add 3 gallons, but then I subtract 2. Okay, so the net effect is I gain 1 gallon every minute. All right, I put in 3, subtract 2, the difference is 1 gallon. Okay, so I'm going to start with 300 gallons, and then I'm going to add 1 gallon per minute. Right, every minute I have a net gain of 1 gallon. Okay, so how many minutes have passed? Well, that's given by time t. If 50 minutes have passed, t is 50. If 2 minutes have passed, t is equal to 2. Okay, so I'm going to add t, because this is 300, the initial amount, plus however many minutes have passed, because I'm gaining 1 gallon per minute. And there we go. This is the concentration. This is the amount of salt, which I don't actually know, right? But the symbol is A, divided by the amount of water, 300 plus however many minutes have passed. And this is pounds per gallon. And here, my unit is pounds per minute minus pounds per minute. Oh, that's good. If they have the same unit, I can subtract. I can't say pounds per minute minus hours per mile. You know, that wouldn't work out. But since they're all the same unit, now I can subtract. So here I get dA dt is equal to, okay, well 3 times 2 is 6. That's a constant. You can put pounds per minute, but now that we know that all of our units do match up correctly, we're okay if we just leave these off. If you want to be very strict about it, you can actually write them in here. But here I'm going to just drop the units now since I know they do match up, pounds per minute, and just leave all of the constants and variables. So this would be 6 minus, I've got 2 times A, okay, so 2A of T, over 300 plus T times 1, because 2 is like saying 2 over 1. So 1 times this is going to give me just this. So 300 plus T. And there we go. This is a model for this scenario. But there is one thing missing here. You might notice here that we never use the 50 pounds. We use the 300 gallons right here in the denominator, but we never actually use the 50 pounds. Okay, so what good does it do? Well, remember, these dynamical systems are going to have an initial condition because these dynamical systems are going to be initial value problems. So that's where the 50 comes in. After all, we're measuring the amount of salt in our tank. Okay, well, how much salt was in the tank at the beginning before any of the water started flowing? At the very first second of this experiment, before any water had exchanged places, we had 50 pounds of salt. Oh, that's our initial conditions. Initial condition is going to be at time 0, the amount is 50. Okay, so the amount at time 0 is 50. And now this equation, along with this initial condition, is our dynamical system. It is our initial value problem, which we can solve to find the amount of salt in the tank at any given time. Well, we can't solve it yet, right? We're going to get to that in later parts of the course. Right now, we're just seeing how to set up these problems. We will revisit this kind of problem later in the next chapter, where we'll actually see how to solve them. But for now, it's efficient to set them up. Let's take a look at one more problem of a similar type. We're going to go ahead and look at another kind of tank problem, but this one's a little different. So in fluid mechanics, there is a theorem, they call it a law, same idea, called Torricelli's law. Torricelli's law states that the speed of efflux of water efflux is just how quickly it leaves. The speed of efflux of water through a sharp-edged hole, nothing tapered, everything's just, it's cut out as simply as possible. Sharp-edged hole at the bottom of a tank that is filled to a depth of h is the same as the speed of a drop of water is the same as the speed of each drop of water is the same as the speed of each drop of water that falls freely from a height of h. Basically, you have a tank. The tank has a liquid in here that has a depth from the top of the water down to the bottom of the tank, has a depth of h. Okay, now you've got a little hole down here that's sharp edged, nothing tapered, nothing smooth, just a single hole that's been punched out of the bottom. The water will now fall out of this tank through the hole. Okay, well, how fast is that water coming out? The speed at which the water is leaving is the same as if you had a single drop of water up here and let it fall. Okay, how fast would it hit this bottom? Oh, it would hit at 20 miles an hour. Okay, well, then that's coming out at 20 miles an hour. If the tank lowers a little, okay, well, now that's a lower height. Okay, how fast would it hit the bottom now? Oh, from here to here, it would hit at 12 miles per hour. Well, then that's how fast it's coming out right here. The height of the tank, if you were to let a single drop of water fall and hit the bottom, that's the same speed that the water is leaving from the hole at the bottom. Okay. All right, well, simply put, that means that the kinetic energy of the water, how quickly it's moving, is the same as the potential energy of the water up top. So here we have kinetic energy. Oops, kinetic energy is equal to potential energy. The kinetic energy of the water coming out is equal to the potential energy of the water up top. Potential energy, which we have equations for. I'm not going to lie, I actually had to look these up before starting this recording because I don't remember these from when I took physics. But once I saw them, I was like, oh yeah, of course, I remember those, just not off the top of my head. Here, kinetic energy of a moving object here is 1/2 mass times velocity squared. And that's equal to potential energy, which is the mass times the gravitational constant times your height. mgh. Where here g is the gravitational constant in whatever units you happen to be using. Here you could solve for v. Go ahead and double both sides. Divide by m. So this gives me what? V squared equals, the m's gone away, so 2gh. I can take the square root of both sides, 2gh root, like this. And this will give me the velocity, isolated, of the water that's exiting. That's the speed of efflux of the water, the speed at which the water is exiting the tank here. And here we're going to do this in feet per second. You can, of course, use any unit you like, but I've chosen feet per second here. Just be consistent with whatever units you choose. Here I'll use feet and second all the way through. All right, now assume that at the bottom, this tank has the hole, and the area of the hole is given by some amount. We can compute the area of this hole, and I've drawn it as a circle, but it can be any kind of hole, square, rectangle, triangle, whatever. But its area is going to be A sub h. Okay, so let's go ahead and write that. Assume that the area of the hole is A sub h, using whatever geometric formula is appropriate here. Then the volume of the cylinder of water, because if there's a hole here, the water's not going to come out and do this. It's not going to flare out and become a different shape. It's going to come out as a single column. You put a little hole here, it'll just drip straight down from the hole. That's a cylinder. Okay. Then the volume of the cylinder of water that's leaving the tank per each second is given by, well, let's see. This is the velocity. This is feet per second. Okay, so if I let 1 second go by, I'm doing this per second, then this is the number of feet that's going to fall out. Right? The velocity at which this falls out is this many feet per second. So in 1 second, this is how many feet fall out. Okay, so I'm going to let 1 second go by, and that's how many feet are going to fall out. This is going to be the height of this thing. The height is going to be the root of 2gh. Okay? So the volume of the cylinder, remember when you have a cylinder, you just take the area of the base times the height. Base times height, which is going to be a sub h times the square root. So it's going to be a sub h times the square root of 2gh. And again, this is going to be in feet. Is that feet per second? Yeah, feet per. No, that's just going to be in. Let's see. Oh yes, that's going to be in cubic feet because this is a height. This was in feet per second. But since we've already measured 1 second out, that's just the amount of feet. Area is square feet, so this is going to be cubic feet. Cubic feet. There we go. It's helpful to keep your units straight. If your units are not what you expect them to be, and you're like, okay, I did this computation, I multiplied these out, and I got feet per second for a volume, clearly I've done something wrong. So units are a good way to keep a little check to make sure you haven't accidentally put in some value where you shouldn't have. Okay, so here the volume of the cylinder of water leaving the tank each second is going to be A sub h, the area, times the square root of 2gh in cubic feet. But since that's the amount of water that's leaving the tank, if that's the volume here, that's the volume that is no longer in here. So we now have a differential equation here. The derivative of the volume of water per unit of time, every second, is going to equal to, that's going to be A sub h times the square root of 2gh. And a little subtlety here, because this is the change in volume of the tank, and every time a column of water falls out, you're removing it from the tank, this is actually going to be a negative value, right? You're losing this much volume every second. So negative there. Okay. And so this would model the amount of volume, or this would model, the amount of volume of liquid in the tank as using the change in its volume. Now, if you wanted to model the height instead of the volume, there's a very small change that you need to make here. Since this is a cylindrical container, let's assume that the base, which it's the same at the top or the bottom, I'll label it up here, but it's the same as down here. Let's say this is A sub W. Okay, so now assuming that the upper surface area, or lower surface area, same thing, that the upper surface area of the tank is A sub W, the area of the water up here, the top of the water. Then remember, the cylinder is nothing more than base times height. So if I divide out by the base, I'm just left with the height. So that's going to be the change in the height with respect to time is going to be this divided out by the area of that base. So that's going to be negative A sub h over A sub w, square root of 2gh. And here we can see a model of the volume, the change in volume over time, or the height using the change in height over time. Now you can even take that one step further. This law in fluid mechanics doesn't say anything about this having to be a cylinder. It simply says if you have a container with a hole at the bottom. Now here we have a cylinder which has got a uniform width from top to bottom, a uniform cross section. But you can change that. So now, using what we've seen already, now consider the conical cylinder. The conical tank. It'd be interesting to have a conical cylinder. A conical tank, and here I'm going to just draw this out. It's going to look like this. I'm going to have a cone, which isn't going to go all the way to a perfect tip here. It's going to stop at a little circle because that's where the water is going to come out. So it's a cone, but I've cut off the tip. Okay, so I've got a cone. Oh, let's see here. I've got, let me go ahead and draw a center line here so it's a little bit easier to label. The line right down the middle. So here I've got 2 inches radius. So this little hole here has a 2-inch radius. Up here I'm going to have an 8-foot radius. So let's do everything uniformly. So if this is 2 inches, I wouldn't want to call this feet. I want to call this inches. So 8 feet would be 96 inches. Do everything uniformly with the same kind of unit. Okay, and then we're going to have a height here of our tank. This is going to be 20 feet, which is 240 inches, like this. And that's the actual height of the full cylinder, not necessarily where the water is. The water might be somewhere lower. And in fact, we'll label the height of the water just H. Right? This is the full container from at the very top. The water is going to be somewhere between the bottom and the top. Here we're going to say that the surface area at the top of the water is A sub W, just like the same notation I had over here, A sub W. That's the area here. And now we're going to go ahead and consider that for a non-constant height, for a non-constant surface area. So notice right over here, we had A sub W was a constant value all the way through, no matter what your height was. So it was just a constant value. But now it will depend on exactly what your height is. You're going to have a bigger or a smaller surface area, higher or lower. But we can easily find that because it's basically just the slope of a line. If I can find the slope of this line, this will give me a way of relating how high up it is to how wide out it is. Okay, so let's go and consider that. Let's take this line right here, and I could use this line over here as well, but I'm going to choose the right-hand side, and I'm going to find the slope. Okay, so the slope of this is going to be, let's see, well, I've got a height of 240, and it's going to go out this way 96, but I stopped too short, so 94. So, slope is rise over run. So rise is 240 over run. That's 96 from the very beginning, but you actually start 2 inches from the beginning, so that'll be 94. Does that reduce? I mean, they can both be divided by 2. So 120 over 47, and that's it. That's as far as it reduces. Okay, so an equation for this line, assuming you had origin down here, is going to be y equals, let's see, mx plus b, right? So I've got my slope right here, 120 over 47 times, and this would be x minus 2 here. Right, okay. So then I could distribute this out, and I could get oh wait, but I don't want y. I don't want to find the height. I want to find this one here. I want to find x from here to here. So I guess I need to solve for x. Right, so I can go ahead and divide this to the other side, and then add 2. So I would have x equals 47 over 120 y plus 2. All right, because that would give me x, which is the distance from the center to the right, and that's what I want. I want to find I want to find the radius so I can find each area. Radius will give me the area. Okay, and all of this is in inches because I use the inch measurements instead of the feet measurements. Okay, so let's see if I've got this value here, this is all in inches. Let me turn this back into feet, because what I want to do is I want to use these formulas that I had above, which were already in feet. So let's see, there's 12 inches in a foot. So if x is equal to this, then to do it in feet, it would be 12x equals that much, 147, oh, not 147, just 47. 47 over 120, y plus 2, and that's going to be in feet. Then I can divide both sides by 12. No, what am I doing here? I've got, yeah, that's going to overcomplicate that. You know what, let's just do it this way. So if this is in inches to go to feet, the slope's not going to change. It's still the same slope, even if it's in inches, feet, or whatever. So you would just go further. So here, let me just change the 2 inches to 1/6 of a foot. So here, ignore that last statement about 12x. So here, x equals 47 over 120y, still the same slope, but now our 2 inches has become 1/6 feet. You might say, well, your slope is not it shouldn't be in feet. Again, slope, it doesn't matter because you can go as far as you need to, inches, feet, miles, whatever. So slope will remain the same, And here this inches is just 1/6 of a foot. Okay, so this x will give us how far out we would go in any one of these at any one of these heights. And here we can even check that, right? At 20 feet, we should get a radius of 8 feet. So if we plug in 20 right here, let's see, 47 times 20 divided by 120 plus 1/6, and that gives me 8 feet. So yeah, that does work out nicely. Well, okay, maybe not nicely, but it does work out. So here we now have that our A sub W, our A sub W is equal to this equation here. This gives us our radius. So the area of a circle with that radius would be pi times that radius squared. Pi times this radius, 47 over 120. Here I called it y, but of course that y is the elevation from here to here, which your problems would be calling h. So we'll say 47 over 120 h plus 1/6 quantity squared. The area is pi times radius squared. That's the area of any circle. Thus, even though this is no longer a cylinder, it's still following Terselli's law, which means it still follows these equations, and thus dH dt, the change in the height of this tank, is going to still follow this equation. It's going to be negative A sub h over A sub w, square root of 2gh, and we can fill in those values. Here, let's see, we've got my A sub w was the one that I just found, this one here, so that's going to be pi times all of this stuff squared, 47 over 120h plus 1 over 6 squared. Our numerator is going to be the negative of A sub h, where that's the area of this little hole down here, which is just a circle of radius 2. So that's going to be pi times, I want everything in feet, so that should be 1/6 squared. 2 inches is 1/6 of a foot. So the area of the hole divided by the area of the surface of the water, which is variable dependent on height, times the square root of 2. The gravitational constant, if you're looking in feet per second, is 32 feet per second on Earth. 9.8 if you're doing meters, but here we're going to do it in feet, times our height, which here we're going to use the variable, not times our height, times our, let's see here. Right. So here we've got, so here we've got 2gh, like this. Let's see, pi's cancel out. This squared in, let's see, that's square root of 64. So square root of 64, that'll be just 8. And then 8 divided by 6 squared times h. So that will give us an equation dH dt is equal to, we've got our negative here. This is going to be 8 divided by 36, which is 8. We can divide top and bottom by 4, so 2 over 9. Yeah, 2 over 9. Then we've got our square root of h here, so that's going to be negative 2/9 square root of h over 47 over 120 h plus 1/6 quantity squared. And this would be a model for the height of our tank, which is no longer cylindrical, because of course it has to follow the same pattern here, based off of the fact that Terselli's law applies to any tank with a hole at the bottom. And so now, instead of having a cylinder where everything's got a uniform width, now we have a variable width, which we account for using this equation in our denominator, or rather using this expression in our denominator. So here we see use of differential equations to model a few different problems using tanks full of fluid. As mentioned at the beginning of this section, there is nothing special about these types of problems of containers full of fluid. It's just we have to pick something to get started, and that's what we see here. So that is it for this topic, and that is it for this section. I hope everyone has a nice day.